thanks everybody for coming. It is my pleasure to introduce today's speaker, Dr. Emille Ishida. She did her PhD at the Federal University of Rio de Janeiro, and afterwards continued to do postdocs at the Kavli Institute for the Physics and Mathematics of the Universe in Japan, at the University of Sao Paulo in Brazil, at the Max Planck Institutes for Astrophysics in Garching in Germany. And currently she's a, she first did a postdoc and currently is a member of staff as a research engineer at the University of Clermont-Ferrand in France. And she's also co-founder of the COIN initiative, which is Cosmos Statistics Initiative, and also part of Fink. And without further ado,
thank you.
Please.
Thank you, everyone. Good afternoon. Thanks a lot for the invitation. I always like to come back to Lisbon every time I can. And today I am going to talk to you a little bit about the Fink broker. And I will start basically, if you are familiar with transient astronomy, the first part of this is going to be a little bit underwhelming, but I hope that the second part will be interesting for everybody. I'll just, so I just wanted to say before I start anything that this is, I'm here talking about work that majority is not mine. So Fink now is a group of around 60 to 70 people. We have people mostly in Europe, but also in the US and Australia. This is, I'm going to talk a little bit. Fink is led by Julien, Anaïs, and myself, but also includes the work of many different people. So I'm just want to acknowledge that there are many people involved in everything that I'm going to tell you here. So please stop me at any point if you have questions or anything like that. So this should be more of a conversation or anything. This should work, but it doesn't, obviously. Yes. So just to set a little bit the subject of what I'm going to talk about, I'm going to talk about transient astronomy here. Transient with the definition that everything which varies brightness with time in the sky. So I will have variable stars, supernovae, binaries, or even like electromagnetic counterparts of kilonova gravitational waves and things like that. So everything in the optical whose brightness changes with time will be a subject, will produce a light curve, and will be a subject of whatever I'm going to talk about here today. So my day job is to work for LSST, which is the Vera Rubin Observatory Legacy Survey of Space and Time. It's a 6.7 meter telescope, which it's being built in Chile. And if we believe predictions in this day and age, it should be ready in 2024. But we all know what deadlines mean in the world nowadays. So let's work with that assumption for this point. The idea of LSST is actually LSST will going to do a lot of stuff. There's a lot of static science. But the huge gain that it will bring to the community is actually in transient astronomy. So it will have some predetermined cadence, and will cover almost the entire southern sky every 6 or 7 days. And you will have repeated imaging of the same area of the sky, which will allow you to study everything that is varying in each different each different spot of the sky. This will generate 1,000 images or 15 terabytes a night over 10 years, if for the initial prediction that the telescope is going to run. For the transients, we expect to find 10 million candidates per night. So at each night, the telescope will compare the image that it took today with an image that it took some time ago, a template image the first time it was there. And if there's something different, then it's going to emit an alert saying, there is something different here, you should look at, maybe there is a transient. We are going to receive 10 million of those per night over 10 years. So all of this infrastructure that I'm going to talk to you about is actually, the goal is to understand how can we possibly make sense of this amount of data that's going to come.
Sorry, American, the telescope?
The telescope is, I would say, 70% American. And then the biggest international contributors are France and the UK. And there is small groups with international collaborations from other countries, but it's mostly American with a strong component of French and UK.
Not ESO.
Not ESO, not ESO. No. But it is in Chile, in any case. So this is just so you can take a look more or less of how this would be over the days passing in the sky, just to give you an idea that there are many things happening there, and our goal is to study whatever is happening with these new things that are appearing in the sky every day. I don't know which telescope is that, but it's not LSST.
There is nothing.
Huh?
There is nothing going on.
There's nothing. Yes, exactly. Just some sparkling. Okay. So what is the data path that in this situation? What is the path that the data takes? You have the telescope. The telescope goes through the entire southern sky one time, and then you have what we call a template. So you have an image of what the sky is today, right? And then in the second round, it goes there and it repeatedly images the same point in the sky. When it does that, you will notice that something new happened. Whenever these things happen, you generate an alert. So an alert is a small package that contains information about this point in the sky and the difference between today and the last time that you were there. You will generate 10 million of those per night, and that's what we call an alert stream. So these alerts is going to be distributed to the community 60 seconds after the image is taken. Again, if you believe the predictions and the promises. Yes, I'm going to explain that now. Yeah. This alert stream is going once every 60 seconds. This alert stream will be sent to brokers. What are brokers? Brokers are software systems who have the task of receive this complete alert stream and making sense of it and distributing these alerts to the community that is interested in one specific thing or not. So the brokers will receive the raw alert stream that is there. And then in the other end, you have the community, which is only interested in the interesting ones, right? So these persons are the astronomers who will actually make some science out of that. And the goal of the broker is to filter this alert stream and redistribute only the correct, the interesting ones to the community. And for this, we use many different techniques. We use a lot of machine learning. We use cross-match with already known catalogs, cross-match with other alert streams. So for example, for multi-messenger astronomy, we can cross-match alerts that comes from the LSST with alerts that comes from a gravitational wave detector or from X-ray emissions or things like that. So all of these are tools that the brokers will construct to filter this alert stream and then pass to the community a lower volume of data. Let's put it like this. So just a parenthesis here that I have to define this. What is an alert exactly? So an alert is this process that I told you. You have an image, you compare with the other, you take the difference, and if there's something interesting from an alert, we call this a difference imaging analysis, right? Because you subtract an image from the other. An alert is not only that. An alert is a data package, contains these 3 postage stamps. So this is the science image, so the image that was taken today, the template image, the image that was that you are comparing with, and one minus the other, and you see that there is a signal in there. So every time that this signal is higher than 5 sigma, you took these 3 postage stamps plus all of the information you have about environment, observation conditions, position in the sky, if you have some catalogs that you can cross-match with these things or anything like that. And also historical photometry. So if I have an alert at this point today, I am going to add the history of photometric observations to that point. So this would mean the light curve until certain point in the past. Okay, so an alert would be only the last point in the light curve, and along it will gather from historical data the rest of the light curves until some time on the past. For LSST, this is going to be a year. So whenever you receive an alert today from LSST, it's gonna come with the light curve of that point in the sky until a year in the past. This is what you will have to work with. And so this is everything I told you until here is is standard, for example, ZTF, which is the Zwicky Transients Facility, which is a telescope, a Schmidt telescope that is working now, use more or less the same systems, okay? The difference is for ZTF, we have more or less 200,000 alerts a night. And with that, you can basically distribute it to whatever wants it. So you can talk with the, if you individual person, talk to the ZTF people and sign a agreement with them that you will not going to use this for commercial use or anything like that, they can send to your house an alert stream. They have hardware capability to do that. The problem with LSST is that it's not going to be possible because the data stream is going to be too big. They have to limit the number of people who will receive the full alert stream. So there was a competition which ended like a year ago. A lot of different groups around the world applied to receive the raw data stream. So this was the groups that were selected to receive the raw alert stream. So there are Babamul, Antares, and Google, which are in the US, Alerce in Chile, and in Europe we have Laser in the UK, Ample in Germany, and Fink in France. So these 7 groups are going to receive the raw data without any filtering. And then they have the task of redistributing these alerts to the community to do something useful out of this. So I am not the main developer of this from the technical side, but what I can tell you is that either ZTF or LSST, at the moment, everything I'm going to show you is using ZTF because LSST is not ready yet. But the goal of us doing all this is to be ready for when LSST comes. So when the data arrives, you process the data with Spark, and it goes to storage. So the user yourself will never interact with the raw alert stream. So this is storage, and then you have a science portal, which is how the users actually interact with the data. And also, if you want to cross-match with other surveys, you have some Kafka communication that goes with that. So just to show you more or less how this is done, I'm going to go very briefly to the science portal so you can understand more or less what you can do out of it. So let me see if this will work. Because obviously, when I trained it, it worked, but that doesn't mean anything. Okay, so this is more or less, suppose that you are here and, for example, you know that there was an interesting alert sometime on the past. You can do a data search and then, for example, come here in help and try to find, there is examples here if you want to do object ID, cone search, or blah, blah, blah. But let's take like one date here, specifically date here. You copy here and then you put the date that you want, obviously. And then you see, you can choose a time window around that point. So here I would say 1 minute because I don't want this to run forever. And then if the internet is helpful, you should see, you should see, okay. Yeah, I was hoping that's what would happen. We will come back to that in a moment. Let me see if I can do other types of searches. No, it's not good. It's up there. Okay, believe me that you can do a lot of things. Okay, so internet permitting, you would be able to do class search. You can, for example, you can ask, give me all of the ZTF data cross-match with things on Simbat, for example, or things on TNS. Or give me all of the alerts within that period of time, or something like that. So when I'm finished doing the questions, I'm going to come back to this because it was working 5 seconds ago. Yeah, see, it was working 5 seconds ago. So let me see if I can save myself here. So for example, in the class, suppose that I want TNS supernova 1A, for example. By default, it's going to give me 100, I think. Yeah, it will not. Anyway, I will do that later. Sorry for this.
No, the internet is working for something.
Yeah, so anyway, I will come back to this later, but believe me, you can do it. If you're not doing a presentation, it works perfectly. Okay, so the point is, suppose that you know the ZTF ID, you know a class, you know, I don't know, some dates, you can do your query, okay? But this is not something, doesn't help if you want, for example, to get a lot of data to do statistical analysis, for example. So there is also an API where you can come here to see all of the schema of all possible classes that you can get. And if you are in a Jupyter notebook, it's very easy. It's just copying, for example, this type of query, and you get, for example, if you have the object ID, it will return to you a pandas data frame with the correct ID that you have. You also can do the same thing for position, right? Ascension declination with a given radius. You can do the same thing for dates. You have a date and then a window of 10 minutes, for example. You can do this in pandas. Or as I was telling you, give me the last 100 supernova 1A alerts that have cross-matching TNS with supernova 1A, for example. These are all things that you can already do with ZTF data. But this is things that are already there. And from the 7 brokers that I showed you before, all of them will provide this type of service. So it's basically which interface you like best. I don't think there is any intrinsic difference when you do those types of queries in any of the brokers. I'm going to talk to you about now how you can take your own science and build a science module, because this is why Fink was built for. Fink was built for allowing you to make very weird questions. If you have a simple question, I want to write ascension, declination, cutting magnitude, blah, 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 basically any broker that you use, it's going to give you more or less the same thing. In Fink, it was especially designed to allow you to make very strange questions, as long as you can write it as a function that inputs the alerts, the output, or a score, or a Boolean, yes or no. You can construct a substream and direct the substream to yourself. Okay, so this is what we are going to do. So this is what I have talked to you before. This we already talked about this. So this is the broker world. This is not your problem. This is the main specialist. This is you. This is what you want to do with the broker. Okay. So you can get alerts from the broker. As I told you now, you got a few alerts, and this is the alerts that have already passed, right? So now your question is, how can I select alerts in the future? How can I get data from the future and redirect to myself only, for example, the Kilonova candidates or something like that? So you get your data from there, and then you can build your own filter. You can cross-match with catalogs, ask for cross-match with catalogs. All of this is possible, or you can build your own science module. So as I told you, your science module will be anything that you can write as a Python function that inputs the alerts and any other parameters or things that you need, and output or a classification score to give you the probability of that guy being of that class or not, and or a Boolean, give me this alert, yes or no, right? So I'm going to give you an example. I'm going to give you a machine learning example, which is an extreme example inside Fink, okay? So normally, when you are doing machine learning, especially, you also always have a training sample, which is a small sample of data from which you want to learn something, right? So you want to learn something from this sample, for which, for example, you have the alerts themselves and the classification. So, for example, you take things from TNS or from Simba that you have classification, and then you learn anything you can learn here, and then you apply there. It doesn't matter how fancy and how difficult the speech of machine learning people do. All they are doing is a map. It's only that. You can make it very fancy, but it's always a map. It's a very fancy way of doing a map from here to there, from labels to pictures or to lightbird or something like that. But normally what you do is you have the train and you have the test. You train a machine learning model to learn how to translate the input to the output. So the light curves to the class, for example. And then you do that until your deadline comes. And then you're happy with your model. And once you are happy with your model, you take your model and all feature extraction, all secondary information you need to make your model work, and then you upload that to the broker, right? So all of these happen in your realm. Once you have your machine learning model, which is just a pickle file, basically with a trained machine learning model, you can upload that to the broker, and you can use any of the things that are already there. So, for example, we already have cross-metric TNS. So you can use that information if you like. We can, you can use classification scores from other science modules, for example. You can always use that type of thing. So for example, just to give you an example, a very brief example, if you have, for example, a kilonova, you want to search for kilonova, right? So suppose that you have a gravitational wave, detection, which normally is a pretty large part of the sky. They tell you it's somewhere in this area of the sky. So you have some right ascension declination cuts on that. But even when you select the area, there's still a lot of information, a lot of candidates in there. So you need to narrow down to see which of these can be a kilonova. So kilonova is a problem because there are no labels. There's only one observation. So you cannot build a training sample from it. So you build using simulations. So you build a simulated data set for which you have light curves and labels. And then you train a simple random forest classifier, and you see that if you look at the parameter space here, you can separate. The blue ones are kilonova, and the orange ones are other things. And you see that the parameter space is able to separate quite well the kilonova and non-kilonova events. So once you do that kind of thing, you come here. So now you have your trained model. Right? So you did all of that in your simulated environment. Now you have your trained model and your feature extraction procedure. You upload that to the broker, and then you're going to be here in the people that are going to receive, for example, I only want the alerts whose probability of being a kilonova is higher than, I don't know, 80% or 90%. You put the threshold yourself, and then this we're going to direct this to yourself. This can be anything. It can be a Kafka stream, can be a Slack bot. We can send emails to you depending on how much emails you want to receive. You see that there are many different ways that you can receive that kilonova. But then after kilonova candidate, because at this point nothing is confirmed, kilonova candidate. If you want to get science out of this, you want to involve domain knowledge experts. You have to get people. So one of the examples that it is that our kilonova stream is redirector for the GRANDMA collaboration, which is a network of professional and amateur astronomers. So they have a lot of people with different setups of amateur telescopes around the world. And during summer 2021, we sent them a lot of candidates. A few of them survived selection cut, and they made a very interesting way of incorporating the work of amateur astronomers and the community into these things. Obviously, none of this is a kilonova, because if it were, you would know about it. But it was a very interesting exercise to understand how you can engage the community of this. One thing that I didn't talk, but it is very important, is that once LSST starts operating, the images are private. So there's a proprietary time, I think 2 or 3 years for the images, but the alerts are public. So you can do anything you want with the alerts. It's not calibrated photometry and things like that, but there's still a lot of science that you can do without needing data rights, for example, for LSST. So this is why we could do this type of thing.
So who can do science with the Kilonova?
During the first year?
Yeah, because you said that people cannot use
the images. Yes, the images,
so
no.
Who can use the...
It's only people who have LSST data rights, which is people in the US, in the UK, and France.
But you know, if there are 10 million.
Yes, it doesn't mean that, most of the data, more than 99% of the data, nobody will never look at it. Nobody will ever look at it. Nobody will, because it's impossible. That's true.
It's going to be from the garbage, right?
It's going to be there. I don't think for LSST we will have storage problems. It's different from SKA, for example. Radio people have the problem that they cannot even store the data that they get. They have to throw it away all of a sudden. For LSST, we still think we can store it, at least for 10 years. After that, I don't know. Depends on funding. Theoretically 2 or 3 years. It's around 2 or 3 years. I don't remember the number, but it's more than 2 for sure. More than 2. But this is, yeah, but this is the images, which is the treated images, right? So with the alerts, you will have the historical light curve for a year, and you will have the postage stamps. These are public. These you can use, and there's no problem. But I don't think the fact that nobody's going to look at them is a problem of the data rights. Even if we take all the people in the world, 90% of the data would never have someone looking at it. Ah, yeah, definitely. I would definitely support that idea. One of the reasons why I prefer working on LSST on the broker side is that the data is completely public, and then you can do whatever you want, share with whatever you want, and put it and do things like this, which was super interesting. Good. Okay, this is one example. And then when you start having a lot of people, different people looking at the data, you start finding weird things. So for example, this is one exposure, which is one exposures of the telescope. And you see that there's a lot of things going on here, like a very weird thing, very bright, and then it's very fast, and it rotates you see the brightness changes very fast. So you think that this is something that is rotating very fast, but it's very close. So the light curve is very weird, and not the light curve because there's only one exposure, but the trajectory is very weird, and it's very fast. We put this on our Slack channel, and there was a very interesting discussion about if this was the spy satellites, because there are satellites that where they are because they are of public knowledge. So we know we can cross match what you get with the position of the satellites. But there are spy satellites that they're not in these catalogs by definition. Maybe space debris. This is our, there was the one that won in our pool that we made. So it can be some space debris that is rotating very fast and is causing this type of thing. I do prefer it was an alien spaceship, but at this point, I cannot say one way or the other.
So this was CTF?
This is CTF.
And you say it was one exposure? How long was it?
I will not invent a number. I don't know. But it's some less than a minute, maybe. I don't know. I have no idea. But I still bet in the alien spaceship. That's what I prefer. But the point is that independently of what I want, the world is not, it's much more boring. So what is happening, this led to a lot of different discussions about what could generate fake alerts, what can fool these images. And this led to a huge development on the detection of satellite blinches. These are not mega constellations. Elon Musk will destroy 1/6 LSST images, but this is not what we are talking about here. Okay, this is not mega constellations. This is normal satellites that are there, and depending on how they glitch the sunlight, they generate 1 point in the peak in comparison with the template image, and this generates a fake alert. So from our estimates, this was like 140 per night that would come from that detection, more or less. So this is all documented in this paper if you are interested, but it's, yeah. With LSST, this is going to be more, for sure. This is still CTF. And then I want to show you, so everything I told you up to now is like like normal machine learning and normal ways of building things. So let me tell you a more extreme example now. So what is the problem when you try to build machine learning models? Because remember that I told you that you always need a training sample, right? You always need a sample that you have a light curve and you have the classification. Then you train a model to make the map between the light curve and the classification. And once that model is learned, you apply to another data set for which you do not have the class. The problem is that statistically, there is an assumption of representativity on this. So this will only work if your training sample is statistically representative of your test sample. And we remember that in astronomy, labels mean spectra, right? So everything for which you have a label, you were able to spectroscopically classify, means that you pointed a telescope and took a spectra out of it. And everything that you do not have a label for is photometry. So it's a very different observation condition, signal to noise, everything is different. So there is no representativity between these two sets. So you basically do not have training enough to know training sample which is statistically significant to answer the question you were trying to pose. So basically, this is what I'm saying. The ideal data situation is that you have a training sample here. You learn everything you can from here and apply there, where you only have the light curves. The real astronomical data situation is like this. So your training sample is absurdly biased and very much smaller than your target photometric sample, for example. There are two ways of doing with this. So in Fink, we do both. One way is using simulations again. So since you don't have data, you have a lot of simulations, and you can make very deep models out of it. So this is one of the models that we have. It's based on Bayesian neural networks, supernova, and it can give you a classification. The classification evolves the more points you add to the light curve. This is one possibility. The other possibility is optimize the construction of the training samples. So think just for a bit that the fact that in astronomy we need spectra to build training samples means that the training samples that we have now were never meant to be training samples. You are taking something that was built for another purpose, and since this is the only thing you have, this is what you are using. But this is not how these things should be made. So the idea of active learning is just to remove the human from the decision part of where do I take a spectra from. So what you have is the most simple scenario of this would be something like this. You have so you start with whatever data you have, very small. I don't know, 5 examples. Let's talk about binary classification. 5 examples of one class, 5 examples of the other, and that's fine. Okay. You train a model here, and then you train a machine learning model. You define the boundaries between the classes. This is going to be very bad because you have a very small training sample and your model doesn't know anything. But then you take this model and classify everything for which you want to determine the classification. Then you are going to come to this label, to this sample here, and you are going to ask, which of these labels would be more informative to my model in case I had the label, right? So I don't know the label of anyone that. But if I had the model, if I could choose one label, which one would I choose to improve my model better? For example, the most simple way to do this, if you are in a binary classification, you choose the guy whose probability is close to 50%. Because if the probability is close to 50%, that means that your model doesn't know anything about that guy. It can be one or the other. You take this guy, send to a human or a machine, in our case, someone who's take a spectra for you and give you a classification. And once you have a label, you put that back in the training sample and do this again. And then you construct your training sample one by one, and you take out the human factor that tends to always point a spectroscopic telescope for something that looks like type 1a supernova. Okay, because that's also what happens. I have talked with people who made this type of decisions, and they tell me if I see something that is sharply rising, kind of blue, or I know it's probably a type 1a, I'm going to take a spectra because we know that's going to be useful for cosmology in the end. But from the machine learning perspective, if you look at 2 points in a light curve and you know it's a supernova, I don't need a spectra. I need a spectra for the other things that are super weird and we have no idea how to deal with them. So we did this exercise. So we took data that was built by all of the data that we have cross-matched with TNS and Simbad. So we had labels, let's put it like this. We started with 10 alerts, 5 1As and 5 non-1As. And then some feature extraction, we added some points there, and we run this loop for 300 times. So in the end, our where is it? In the end, our training sample had 310 objects only, and the test sample had 52,000. So you see that the order of magnitude doesn't need to be the same if the labels that you have are informative. So this is what happens. So these are completeness, recall, I think, so efficiency, purity, and figure of merit. So this is the number of supernova that exists that you correctly target. So if you say everyone is a type 1a supernova, this guy will be 100%, right? Because you are saying that everyone is a supernova. Purity is from the type 1a supernova that you selected, how many did you get right? So what is the purity of your photometric classified sample? So you see that in the beginning, the code tells you that everyone is a supernova 1a because you see efficiency is super high, but purity is super low, meaning that you have a very high contamination. figure of merit is just a multiplication of these two with some weighting because false positives are bad. But independently, the only thing that matters is that you want these things to be as close to 1 as possible. So being higher is good. These numbers by itself, they don't mean anything. They just mean in comparison to each other. So the blue thing here tells you what does it mean, what does it happen with your matrix every time you do this thing using an active learning scenario, as I told you, making the informative decision every time that you make a query. And the orange one is random sampling. So you at each iteration, you took something from the target and put it on the training, but you didn't make any thought about it. You just take a random one and put it there. So just so you see that there is a significant difference if you make an informative decision about what you are doing there. So this is you see, it can be as complicated as you want, but in the end, what I have is a training sample, I train a model, I have a pico file. It's the same thing that everything else. So if I do everything that I told you, I have a pico file plus my feature extraction procedure, I upload that to the broker. Here I use a cross-match catalogs that I told you that we have already used. So if this thing has already been classified by someone, you're not going to report again. So turn that off. And we require this to be in agreement with the supernova case, because the supernova is supernova, non-supernova. So type 1a is a subset of that. And then you go there and you send this to the early supernova people. So what we have been doing is we do all of this here. And then this stream is every alert with the probability of early type 1a supernova classification close to 50%. Since November 2020, we have been sending these candidates to TNS. So TNS is a repository where the transient name server, and people go there and report classifications and transient candidates. We have reported 4,600 candidates. From this, 573 have been spectroscopically classified by other people, and 80% of them turns out to be type 1a, which coincidentally is exactly where my purity ends there in the estimation. Of course, we need to take all of this with a grain of salt because there's still a human here, right? We send the candidates to TNS. The people have a list of things that we think are type 1a, but there's still a human that looks at the light curves and decides if they're going to take a spectra or not, and that we cannot control. But let's say that is encouraging, that is more or less the same thing. And all of the other things that are contaminants are other types of supernovae. And for some reason, there is one luminous blue variable there, which is the different contaminant. Okay, so after all of this, how can you get alerts plus that added values? So you will see that in the schema, I will put here all the links, but you have early supernova 1A classification. So you can say, give me the latest 200 alerts associated whose probability of being early type 1A supernova is higher than 50%. It will give you a pandas data frame with all of the data that you want. Basically that. So this is so you can understand how you can use the data now. But remember, now we are still working with ZTF. With LSST, all of this will need to be automatized because I cannot like send and have some person looking, it's not gonna work. So with LSST, we are working with the TOM group, which is, TOM stands for Target Observation Manager. So this list is gonna go to a system which has spectroscopically telescopes register in it. And the system will distribute according to available spectroscopic time in every different telescope. Then once someone analyzes the spectra and gets you a label, there's a Kafka stream that will redirect all TNS reported labels back to the model, which will be in Lyon, in Centre de Calcul in Lyon. And the retraining of the model will be automatic every time an informative label is arriving. And then we don't have to touch it anymore. Yeah.
So what Tom means if you didn't say what
Fink doesn't mean anything, it's just a name. No, no, it's just a name. And I don't even have a nice story to tell. It's just Julien, which is the main developer. I don't know why he chose the name, and we thought it was nice, so it stayed like that.
somebody asked.
Huh? I asked him already. I think I will invent a story because that's going to be more compelling. Yes. No, Fink is just so yeah, I'm almost finishing. So this is just so you can have an idea of how these things are going to evolve once we have once LSST comes to life, right? And I want to just a very small thing that I want to tell you is that the same idea of getting the expert come back. What I want to remember from all of this is that machines are amazing, machine learning is very good, but you still need a human to tell you what is important and what is not. Even though I am making the machine choose, the classification is still done by a human. The point is to minimize the times that a human has to look at the data, but you still need a human in there. That is important for the classification, but it's even more important for anomaly detection, because I can give you a list of objects that are anomalous in a given data set, which mean absolutely nothing. They are statistical anomalies, but they are like the CCD gone wrong, there's a satellite on the top, there's an asteroid passing by. These are all statistical anomalies, but they are not scientifically meaningful. You can use the same idea of the active learning loop that I told you about, but here, instead of asking for someone to give a class, it's a 1A, it's a 1B or something like that, you can ask the expert, is this an anomaly that you are interested in, yes or no? And then if the expert says no, you go back to your model and you redistribute the weights of your random forest and do the thing again. So the code each iteration becomes more adapted to the kind of anomaly you are looking for. We have results on this, and I don't have time to talk about it, but it's super interesting. And we hope that this will be on Fink as well. We have people working on implementation for this. So just to finish, because my time is almost over, I told you about kilonova, satellites, and supernova just because of time constraints, but Fink has microlensing, multi-messenger astronomy. We are working on omniscience. We have solar system. So whatever you want to do, it's possible to do. Sometimes it's going to be a little bit difficult, but the earliest you tell us, the better, because the system is really being constructed right now. So it's very easy to adapt. And I will leave you a few links if you want to access the data and play with it, and be more than happy to answer your questions if you write us emails or if you want a substream or something like that. And one thing that I didn't tell you is that in comparison with the other brokers, Fink is very new. So 3 years ago, I didn't even know what a broker was. So Fink was born in 2019. And different from other brokers, it's not a broker that was like built for another system and it's going to be adapted for LSST. The difference is that Fink from the beginning was built for LSST with active learning in mind. So all of these active learning strategies that I told you about, I'm doing for supernova just because I did my PhD in supernova, so I have a supernova background, but it could be adaptable to any kind of target that you want to get. So just my final message, I want to tell you that if you have to forget everything I told you here today, I just want to remember that there's a lot of science that can be done, even if you don't have LSS data rights, especially if you have access to some spectroscopic, some follow-up facilities. Most of the data will never be seen by humans. But this is not a problem. This is an opportunity, because if you go inside the data with the correct tools, there's definitely a possibility that you're going to find something nobody ever saw, because most of it nobody ever saw. So just look at this as an opportunity for the future, and I'll be more than happy to take questions.
So questions. Okay, then if oh, sorry. No.
Do you have so you have catalog matching to GRBs or gamma ray burst or X-ray stuff?
I am not sure if they are deployed, but there is a tool that you can upload your own catalog. Okay. If it's obviously there is a size limitation, but it's pretty big. So if you have your own catalog, you can upload your own catalog and cross-match your own catalog. If it's too big, the only difference is that you have to send us our catalog, and then we have to share the catalog somehow. And also needs to be public, because everything needs to be public if you have to send it to us, but it's possible to do. We have been we have very close connections with these Iswan people, I think, in order to try to cross match both alert streams once Iswan is producing something. So I am not sure if they are public now, but you can definitely do that if you have a catalog in mind that it's not there yet.
Other questions?
Can I ask a question?
Yeah.
Okay, let's do you afterwards. Okay, Ariana, is okay? Let's. Yeah. Yes. Please do.
Alex, can I ask a question?
Yes, you can. Please go on.
Yes, please.
Okay. Hi, Emily. Thank you very much for the talk. It was very nice.
Hi, hello.
I have one question. It was not totally clear for me. How are you able to classify a supernova? Meaning, what do you require, or what does Fink require to classify a candidate as a supernova? Can you do it just one data point from ZTF?
Yes, I didn't talk about that, but no. And this is a very good question. So what I didn't talk about you was the constraints on feature extraction. So I talked very briefly about this. The goal of this data is to get early supernova, meaning that we want things on the rise. So before an alert can get into this loop, what we require is we make a derivative calculation. We take only points that are going up, right? And from the points that are going up, you need 3 points in each band. It can be a non-detection. A non-detection would be okay, but you need 3 points in each band. And then we do a sigmoid fit with these 3 points, and this is the fits that you are seeing here. So you need at least 3 points in each band in order to be able to produce these classifications. And this is basically one of the biggest differences between our 1A classifier and other brokers, because normally we have a much lower number of candidates because we require more information. Yeah. So if other brokers give classifications with 1 or 2 points, we don't do that. So our data, our candidates will be lower in number, smaller in number, but the accuracy rate is higher. But there is no way to get out of this, right? So you win in one side and you lose in the other. Did I answer your question?
Yes, sure. Because I mean, I used to work for LS, and we used to classify supernova candidates, but we not classify the type of supernova. That's what I was concerned.
Yes.
Thank you very much.
Yes, no problem.
Thanks, Anna. So now I think Ariana, you had a question.
Yeah, it was just about the curiosity to say that it's already southern hemisphere, right? So
the honest question is I don't know, but I know that there are people working in galaxy related things. So we are definitely going to image the galaxy to some level, but I don't know. I cannot tell you to which level.
I think it does. No. Galactic center, yes. You can see it from the south. Yes.
Yeah.
Thank you for the presentation. Can you re-explain the start where you select training set?
Yes. Yes. Because the point is like that. You have a light curve, right? You have like 2 points in a light curve, and you have to decide if you are going to take a spectra or not. If you are a human, you tend to choose things you know, because telescope time is very expensive. So you will normally try to get a spectra of something that you know it's going to be useful for some science, right? So if you are a type 1A person, you are going to be very quick to classify a rising type 1A light curve, and you are going to take a spectra of that. If you are an AGN person and you can quickly define that is an interesting AGN, you are going to go there and you're going to take spectra of that. The end of this process means that you are populating your training sample, because each one of these spectra is a label, with things you already know. And this is not what you need for the machine learning exercise. So here, when you do this loop, every time you come here, you take a classifier, you classify your entire sample, and instead of going to the objects that you know the most, which would a human do, what we get here is what is the one you have no idea about. So take the 50% ones, right? It can be one class or the other. So from the machine learning perspective, what you are doing is you are probing the boundaries of the classes to better define how the boundaries are decided. Yes, so you are going, sorry, say that again. Yes. Yes, yes, because what the machine is looking for is things that are statistically informative to the model, right? So what are the information that I do not have in my training sample now? When you do this, by definition, 50% of the things you query, and so the things that you ask Spectra for, will be of your positives class. So in this case, 50% will be 1As, because you are querying things with 50% probability of being 1A. So if everything is right, you're going to have 50% 1As and 50% something else. But it will not be any 1A. It will be 1As that are easily mistaken by other types, and other types that are easily mistaken by 1A. So you are making a selective choice of going to the boundary of the classes to improve your classifier. Is that clear?
Other questions? If I may ask one, very naive one, because I don't know a lot, hardly anything. So what makes, so you say that the Fink broker is designed, say, for LSST data. Is it just the amount of data going to be received that is going to make the difference, or is anything else specific about the LSST?
Yes, so the schema for ZTF was on, the schema for LSST was on purpose built to match ZTF as much as possible. So the huge difficulty will be data volume, basically, to deal with all of that. To make a query, how do you query 10 million things a night and doesn't take 5,000 years to give you an answer of it? So all of those things are the problem. The schema itself is going to be very similar, but obviously things are going to be, but ZTF is considered a precursor of LSST. So most of the things are meant to be transferable from one another. But obviously there are details of the infrastructure that's going to be updated. Thank you.
Last round of questions.
What do you think is the big difference with other brokers besides the capability of Fink to set up your machine learning, let's say?
For people who have data rights, Fink is going to be hosted in the CC in Lyon, and by the agreement that France has with the US, a full copy of the data will be in Lyon. So for people who have data rights, they will be able to cross-match the alerts with the images in the same location, because the data will be already there. So that's also one of the other differences that's going to be there.
Okay. So
just so you know what I did here. So I did a class search and I asked for the early supernova candidates. It gives you wide ascension, declination, blah. There is an entire list of things that you can add to that table. So for example, if you wanna add CDS crossmatch, it's gonna tell you the CDS crossmatch classes of all that. You can query the table itself. So suppose that you want only things with right ascension lower than 290, for example, it's going to give you this. You can go to SkyMap and it will tell you the distribution of the alerts that you're seeing. Yes. And if you come here in preview, I hope this will work. You can have a preview of the first 10 alerts that satisfy your query, you see, and you can, it's like Tinder for transients. So you can go there and see what's happening, and it also works in your phone. I tested, it works in your phone, so you can also go through the live of the phone. And then
you have the app version, or
no, it's the web version for now, but yeah, but it's on the plan, it's in the to-do list. And then if you want to come to, if you have the specific name of ZTF, for example, You can come here and you see you have the light curve, you have some contextual information, you have links for TNS, Simba, the SNAT viewer, and also like location and things like that. And this is just the summary. If you come to the supernova tab, you will see that here you can see the machine learning scores for the 3 different machine learning models we have. So this is like, one is a supernova score, and the supernova score and 1A score are the deep learning ones. And the purple one is the early supernova classification that I told you about. So you can see how the scores evolve with time. And you see, as I told you, the early supernova classification is always late. The other ones get it first, and then it takes a longer time to make a decision about something. But it's always. And if this was a variable star, you could also like fit a variable. There's a microlensing, blah, blah, blah. So anyway, now it's working, so I wanted to show you.
Awesome.
If you enjoyed the video, like and subscribe.